Hey folks, here's some notes on limits involving infinity. Basically, we've been taking limits for a constant here. The limit as x approaches 2, or the limit x approaches -5. But now we're going to look at what happens way, way, way out to the right of your graph and way, way out to the left of your graph. This is also called end behavior. End behavior is as x goes to infinity or as x goes to -infinity. So it's what your graph does way out to the right and way out to the left, which is also interesting stuff, especially because we're going to be graphing these things in the future. Here's a way to check for horizontal asymptotes. Remember, you know what vertical asymptotes look like because we did those in continuity, right? So if you have like a vertical asymptote, you'll have a graph that, does something like that, right? Well, if you have a horizontal asymptote, that is the line, a horizontal line your graph approaches way out here, way out to the right, and way out to the left. Now what's different about them is vertical asymptotes can never be crossed. Like you'll never cross that. Horizontal asymptotes are a little more lenient because you could say the horizontal asymptote of this line is 1, and early on it might cross it, like that. And then maybe it just approaches it way down with really huge numbers, and over here, let's say it approaches it with really huge negative numbers. So anyway, it's going to be useful later on when we graph. So a couple things. First, it's useful to write your number as a fraction because if you look at your fraction and the highest power of x is in the denominator, I call those bottom heavy graphs, then automatically your limit as x goes to positive infinity and negative infinity is 0. So, for instance, this guy right here, okay? See how x to the third is your bigger power? It doesn't even matter what this is. As x goes to infinity, the value of this goes to 0. And it seems crazy because imagine plugging in an infinity there and plugging in an infinity there. You're like, oh my gosh, I'm going to take infinity squared and then I'm going to put 4 times that. And that's a huge number, but the amount of hugeness that comes out of this is so much bigger that it's amazing. Same with this plus 50 and minus 85. Do you know what's cool about this? They don't matter at all. And I'll show you a quick example on the calculator on why they don't matter at all. Imagine I even used a number like 1,000. And 1,000 is not even close to infinity, right? So let's say I have 4 times 1,000 squared on top. That is 4 million. Okay, so the top number is 4 million plus 50. Do you see how insignificant the 50 is already? Right? Instead of 4 million, you have 4 million and 50. It's already insignificant, and that's with x is 1,000. Imagine if x gets close to infinity. The 50 becomes less and less important, and it has less and less effect. But what I'm telling you is the 4x squared is not even that big of a number. Even though it seems huge already, it's already at 4 million. Imagine what 1,000 to the third power is. Here's what the bottom is, just at 1,000. Oh my gosh. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's a trillion. Okay? Because here's a million, it's 1,000 million. So already the bottom is getting so huge. And imagine if I took away 85, how ridiculously insignificant that is. Oh, now I'm only at 999,999,915. So you can already see how useless constants are as I go way out to the right and way out to the left. You can also start to see how useless even a lower power is because you think, man, 4 million is a big number. Not compared to 1 trillion. And that's only at 1,000. Imagine if I used like 10,000. and I squared it, and I did times 4. The top is going to be 400 million. And you're like, oh my gosh, 400 million is a big number. Well, guess what 10,000 to the third is? This is how much, oh my gosh, it's a 1 with 12 zeros. I don't even know what number that is. It's huge, okay? 12 zeros. So you can see that the bottom is going to win out. Well, what happens when you take a number, actually let's do these two numbers divided by each other, because it's like the top divided by the bottom. So if I took 400 million, oh, why am I even typing this? Hold on, let me just go grab it. 400 million divided by that number is 4e negative 4, which means 0.0004. It's already this tiny. The bigger the number I have, the bigger the number on bottom when I cube it. So I'm dividing by a larger and larger number, and essentially I'm turning it into 0. The limit of this is 0 because it's bottom heavy. The other way I like to do it is I like to just grab the first term of each, right? So I'm grabbing these two, and I cancel stuff out. Like I pretend the 50 and 85 don't matter, because at infinity they don't matter. And I'm just going to simplify this. So if I remove those, I have 4x squared over x to the third. Now since there's no plus or minuses, I can actually cancel off 2 of these guys with 2 of those guys. And it becomes the limit as x goes to infinity of 4 over x. Well, guess what happens if you divide 4 by a larger and larger number? 4 divided by 100 is 0.4. 4 divided by 1,000 is 0.04. 4 divided by a million is 0.004. 0.00004. So you can kind of see another reason why the limit is 0. Anytime you have a bottom heavy graph. Okay, so that took care of that. Anytime you have a bottom heavy graph, it will approach 0, which means if I graph this, I don't know what it's doing early on, right? It could be wiggly and stuff like that, but I do know as you go way out to the right, it goes down to negative, or to 0. As you go way to the left, it's going to go to 0 too. But this one only asked about the right. See how it's positive infinity? So I know if I go way, way, way out to the right, it's going to get closer and closer to y equals 0. Okay. So that's for bottom heavy ones. If you ever see a graph that's top heavy, it is going to go up forever or go down forever. It's not going to go to 0. Basically, we call these unbounded. And you have to be careful on whether it's going to go up forever or down forever. Sometimes you got to use your common sense. Sometimes you could just plug in a big number or small number to decide to determine if it's going to go to positive infinity or negative infinity. So positive infinity are those graphs that, go up. So imagine I was graphing just like y equals x squared, right? That goes up to positive infinity as I go way, way right. And as I go way, way left, it also goes to positive infinity. If you looked at your cubed graph, it looks something like this, right? So as I go to positive infinity, the limit is positive infinity. As I go to negative infinity, the limit's negative infinity because it goes down forever. So that's just some things to consider. Usually, I know in the past I said if it goes up forever or down forever, the limit does not exist. Technically, the limits on these is DNE, but we can be more specific and say not only does it not exist, but it goes up forever. All right, so now that's bottom heavy. That's top heavy. So let's look at a top heavy graph. Here's one. You got this guy. The highest power of x is on top. A lower power is on bottom. And these 23 and minus 1 don't even make a difference. Think about it. If you plugged in a million here and cubed it, do you think subtracting 23 makes a difference? Answer, no. And what's also weird is, even if this is a million for x, and that's 4 million on bottom, the top is so huge that this doesn't even matter. So you could really treat it like you had 3x cubed over 4x, and you canceled out one of the x's, and you get 3/4 x squared. Now imagine plugging an infinity in there. I know you can't plug infinity in, but imagine you plugged a ridiculously big number and squared it, and then took it times 3/4. It's still ridiculously big. So as x gets bigger and bigger and bigger, this whole thing gets bigger and bigger and bigger. So that is positive infinity. If I looked at its graph, I don't know what it's doing early on. There could be asymptotes, there could be all sorts of stuff. But I do know as I go way out to the right, my graph goes up because that's positive infinity. Okay? And the last of the three cases, and then I'll do the examples on a different video. The last three cases is, well, if I have bottom heavy and I have top heavy, what about equal weight ones, right? I call that equal weight. Well, equal weight ones are special because you actually get a number answer. I mean, 0 is a number, but it's, it's a special number. You get like all sorts of number answers if they're equal weight. So you take the coefficient of the highest numerator's highest power and the coefficient of the denominator's highest power. And that is your horizontal asymptote. So here's an equal weight one. Remember, I am just looking at these two numbers. Be careful if they're ever out of order. But this is insignificant. This is insignificant, right? Imagine putting 1,000,000 in here and cubing it. -1 doesn't do anything. Heck, even minus or plus 3,000,000 doesn't do anything. So because of how huge infinity is, it's kind of cool. You get to ignore all that stuff. And your problem boils down to just 4x cubed over 5x cubed. Well, if you reduce that, you're just left with 4/5. That's your limit as you go way, way out to the right. And it's positive because you have a positive over positive. If I graph this, once again, I don't know what it is doing early on, but I do know, here's about 4/5, that way out to the right, my graph is going to get closer and closer to 4/5. I don't know if it's coming from above or below, but I would have to use some more points. We'll do that later in the year. Anyway, I'll come back and do some examples, but hopefully you understand the three cases. Bottom heavy results in 0, so it approaches the x-axis. Top heavy is unbounded, so it either goes up forever or goes down forever. Kind of like this. Top heavy graphs go to infinity or negative infinity. We'll talk about how you figure that out later. And if they're equal weight, you just basically cancel stuff off and save the fraction that comes out. All right, I'll come back for some examples in my other video.